Okay, so that brings us to our next speaker. Our Bob will describe some of the work he's doing on more stuff in neural networks.
All right, thanks for that, CJ. So I'm going to be talking about learning policies for mobile robots using a special class of networks that we call memory augmented neural networks. This work is a culmination of 2 years of work. So it's not just something that I've done for the thesis, but it's something that I've been doing from 2016. Okay, so deep learning works really well for state-of-the-art image recognition, speech recognition, and all these other challenges that we've been able to do in signal processing with deep learning. What we like to do in this is we like to learn some of this impressive performance and bring it to robotics. We like to learn what we do in robotics is perception action loops. We perceive the environment, we process it, we plan some trajectory or execute some control action, and then figure out how we're trying to achieve some goal with robotics. So deep learning, we're trying to bring the promise of deep learning to robotic planning and control. So and this has been investigated over the last 2 years or 2 or 3 years, and just so we know where do we stand. So this is actually from 2016. What this robot is doing over here is trying to learn how to put that peg inside the little hole over there. And what it is doing is basically, and it's got this little camera over here, which just keeps sensing which senses the the position of its peg in the hole. And what it's doing is trying this again and again for 1 billion times before it actually gets there. So this works pretty well, but this is not a mobile robot. You can have this grasper sit on a desk for 10 days and just keep trying this again and again and again. You don't have battery constraints, you don't have power constraints. You can just plug this in and learn some sort of linear Gaussian controller, and you keep doing this again and again. And you can do reasonably complex tasks with this. Okay. What we want to do here is we want to learn how to do these planning tasks, which are long-term sequential tasks, and we want to train a neural network to do this. So we've got this complex environment that we're trying to navigate from a start position to a goal position. We assume no information about what the environment actually looks like or any prior knowledge about the environment. And we're trying to train a neural network to navigate this complex environment. Okay, so an MDP is this Markov decision framework that we use. You've got a fixed start and a goal state. You can vary the goal state, or you can actually vary the start state also. At any given point in time, you only have some sensory information, which is the local information. You don't actually know what the entire map looks like. And what you also want to do is, with robotics, if I designed a policy or control action, it would work in one environment, but it would also work in all these other environments. That's not always true with deep learning, because if I train on some data set, it doesn't actually work on the other data sets. So we want to actually see if what we're learning can actually generalize to other environments also. And then there's this other problem that because the environment's unknown, you don't actually get any sort of information from the environment until you get to the goal. So I have no idea if I can't use a heuristic like, oh, I'm getting closer to the goal or I'm getting away from the goal. I only get information when I get to the goal. So just writing this out, we call this problem the feasible path planning problem. So you've got some states, you've got some you've got a goal state, you've got a start state, you've got some some obstacle occupied states, and you got some free regions. You've got some motion model, and you've got some observation model. And then the problem statement can be defined as, given an initial state, you want to find control policy such that applying that control policy over time gets you to the goal state. Okay. Just a little bit of notation. So a Markov decision process, you can write it out as I, U, T, R, and gamma. I is your state space, U is your action space, T is something we call a transition function. So this actually encodes your motion model and your dynamics model. What it tells you is given a state and an action, what's the probability that you will end up in this other state. R is your reward function, gives you some reward over whatever you're doing. Gamma is some discount factor. What it serves to do is it's discounting future rewards more than current rewards. If I give you 100 million a year later, that's worse than giving you 100 million right now. That's the analog of the gamma over there. Okay, so using fully connected networks, you can do something like this. And this has been used for Atari and works really well. So you take in some fully connected network and you output something called QSA. So what this is telling you is how good is it to take a certain action in a certain state. And you can learn this. You can try and learn this for something like this. And this has been done in Atari, and this works really well. So this is actually called DQN, and where you do this convolution over all these images, and you try to learn some Q-value function. So the problem with this is in these partially observable environments, because you don't have any reward from the environment, you just keep exploring. So this blue thing over here is the robot, and it's trying to get to this red goal target. Because I don't have any prior information or any information about where the goal is or anything of that sort, I can explore the space forever and I'll never actually get there. And this is what we're seeing over here. So in these two, the difference is for this, I'm only feeding this tiny little dot over here, which is the sensor map. That's fine. And for this, I actually stitch together all the things that you've seen before and try to feed that to the robot. In both cases, that doesn't work because it's unreasonable to expect that without any reward, it'll actually converge. And then you've also got those local optima. So you've got these little things over these what we call as local optima. These tunnels over here where you can get stuck and you need to figure out. So this is actually a really good spot because it's right next to the goal. But the problem is you can't actually get to the goal from here. So this is the local optima that we're talking about. So reinforcement learning, you have some convergence guarantees. Supervised learning can solve sparse rewards efficiently. Can use a mixture of reinforcement learning and supervised learning to learn our policies. So a little bit of background. People had something called value iteration networks. So if you look at the equation for value iteration, which is this iterative way of updating value for each state, and if you look at the windowed convolution equation, you can see that these, like this term and this term is analogous. So v of x is your last value, kx is some kernel that you learn, and px dash x is the motion dynamics or the environment dynamics that you want to learn. So what these guys showed is you can approximate value iteration by doing windowed convolution, and you can learn some value for every state in your environment. So what we want to see if we can leverage this idea and learn some value for each state, and then the problem with this is with this environment over here, the entire map is the input to the algorithm. Now, obviously, we're dealing with a partially observable environment. We don't actually have this entire map. So we're thinking about how do we store some sort of temporal information. So in robotics, this is called SLAM. You build a map and you have access to that map at all points. Instead, we're saying let's have some sort of memory representation. And let's learn at what points and what information to store in that memory as part of our learning process. To that end, we're using something called a differentiable neural computer. A differentiable neural computer is this new architecture that learns how to take some input and correspond that to an external memory bank. So it outputs three things. It outputs a read weight, a write weight, and a access weight, and that is used to access this external memory, and they make sure it's differentiable, so you can put it inside an end-to-end differentiable scheme. So putting it all together, so this is you only take in this small tiny input over here. You do some low-level processing. You do this value iteration over it. You calculate a value for each state in it. You feed this into a controller, which has access to an external memory, and then this external memory also has access to everything over time. And using that, you output some sort of policy. So when we were talking about generalization, and so what we want to do is we want to learn how to plan inside this small little tunnel. So your observation is only this little thing over here, and we're able to do this on small tunnels. But the idea is, if I taught you how to navigate one tunnel, you should be able to do any tunnel. And this is what we're showing over here. So because I've learned what the topology of a tunnel looks like, by training on those small size things, I can actually extend to larger and larger tunnels, because a tunnel is the same, it's just this is longer. And this is really cool because it's never actually seen this in its training set. This is a completely new tunnel. It's longer and it's much bigger. And we see that we can keep making this bigger and bigger, and actually it fails over at this point. So this is like really long. This is about 200 or so meters in length, and this is where it actually fills. And it's reasonable because memory is still a bottleneck at this point. So going from here to here, we didn't actually change the memory. Going here, we still didn't change the memory. The size of the memory is the same, but at some point it's going to be a bottleneck. Okay. So now what are the drawbacks of this method? We trained that with supervised learning. Obviously, the problem in robotics is you can't always generate these supervised labels. For example, if you're playing this video game, you can have multiple policies. You can shoot this monster coming at you. You can jump back. You can run away. You can do all these things. If you're trying to navigate this environment over here, you could either take the right path, left path, and you'd still get to the goal. So this is the problem with supervised learning. If you give conflicting options to the same label, you're gonna have your training is going to be unstable. So we're saying reinforcement learning is a good way to solve this. And the problem with reinforcement learning that I talked about before was you can't actually do reinforcement learning because your rewards are sparse. Turns out there's a lot of things in the environment that you can also model. You don't have to depend on the environment to give you a reward. So in this, we're modeling 3 different things: state prediction, reward prediction, and action prediction. So at every state, I execute an action, I get a new state. I can exploit this information, and I can. What we're saying here is, given the state, given the action you took, can you predict what the next state's going to be? Given the action, given the next state, can you? Given the action, given the next state and the current state, can you predict what the reward was? And given just the 2 states, can you predict what action took you? So these are some auxiliary rewards that you're using, and we show that these can be used to learn to, or rather guide your policy, because in some way these are updating your belief of your agent. So putting that together, we're extending that architecture we saw before. So you've still got the value iteration module, we've still got the memory module. This is actor critic. This is just learning a policy using temporal difference. What this is doing over here is this is learning your auxiliary rewards. And to see how this works, so we're playing this Doom game. We start over here and here, and we're trying to get to this red star over here, which is pretty far away. Doom's actually a reasonably easy environment to learn things on. So, the last thing over here you see, it's like it starts from this point and learns how to navigate all the way over here to that green jetpack over there. Doom's easy because it's got all these textured walls. It's easier for a network to remember. It becomes more challenging when you try to do this for robots. And this, we're testing with 3 different environments. This is, just some test environment. We're trying to use a LiDAR scan, trying to get to this goal. And this is actually a vague model of what living looks like. And these are actually harder because now you have a LiDAR scan, which can be noisy and sparse, and you're trying to use that to get to your goal. So, with all these, we show we're actually able to get there. What's more interesting is also we put this on a real robot, and we show that you can adapt from this policy that you're using. And so for this case over here, we train this in simulation, then we take that policy, and we're training it in, we're testing it on the real robot. So it's just this tiny setup, but it's still a proof of concept that it works. And over here, you've got this big chunk over here that's sometimes there and sometimes not there. What the robot needs to do is it needs to learn that every time I see this big block, I need to take the longer path and get to the goal, as opposed to taking the shorter path. And that's where it actually uses its memory. All right, so what are the next steps that you can extend from over here? The obvious idea is you want to do this because we have a multi-robot lab. We want to take this from the single robot and extend this to multiple robots. So this is a simple problem that we can think of is, you've got all these agents and they're trying to get to a goal without crashing into each other. Can you actually learn how to do this with your shared representations that your memory module is learning? Another problem that our lab did in 2014, this is CAP, concurrent assignment and planning of trajectories. You've got these robots, and this is an NP-complete method where you learn some trajectory that does not crash into other people's. So you're doing goal assigning and planning. So can we actually learn how to solve this with deep learning, or rather with the memory augmented network we're proposing? The problem with those traditional methods is they're super constrained, and anytime you add a simple constraint such as start orientation needs to be fixed, or your goal orientation needs to be fixed, it ends up crashing. So this is actually something simple that we were able to learn. There's all these moving obstacles, and there's this wall with the moving obstacle, and we're trying to have the robot follow a simple trajectory. So just by looking at whatever local, it gets some local information, and it's able to learn actually what to do with all these moving robots. So this is a simple case. We're only trying to learn one policy, and we're trying to avoid all these other robots. We're doing this with reinforcement learning. So we're just like tracking different trajectories. We're tracking a line, tracking a circle, and every time the obstacle comes near, it learns to deviate a little bit and then come back to its path. Then there's these other collaborative tasks you could learn from multiple agents that you could extend these. Now you've got these predators and preys, and somebody's trying to chase the other agents are trying to run away, and there's all sorts of obstacles. So this is something that we're still doing. We're not there yet. And then this is what the architecture for something like that will look like. So you've got all these inputs from all these agents. You learn some shared representation over it, and then you output some policy. And yeah, we're still working on this. And this is future work, so hopefully external memory is a good way to go with multiple agents. All right, and thank you for everybody who's collaborated on this work. Thank you.
Okay, fantastic. Time for a few questions. What did you comment a little bit on the role of sort of memory in all this? That seems to be a key feature.
So the problem with this is, if you're doing this task with just something like convolutional networks, the problem is when you're going in and you're coming out, this observation is the exact same. So if you think about learning, if you map the same input to two different outputs at different times, you're going to get messed up. Your learning's never actually going to converge. So you want to learn some sort of sequential history-based thing, and that's where memory comes in. So you want to learn. You want to learn that, okay, when I'm going in, I want to learn to store all this information. When I see that dead end over there, I want to learn how to use that memory and read back from it until I get out of the goal. So that's some of the memory ablation stuff we've studied, and we've seen that you can learn how to condition on your past states, as opposed to and the interesting thing is you don't want to store everything. You want to store only some things, and you want to have your memory learn how to store some things.
The other question is that for some of these tasks, there are reasonably good approaches that are more classical. So you could argue that they will have maybe kind of performance bounds. Have you looked at comparing outputs or using inputs from the traditional planning system to help train and or guide?
So this is actually trained with A-star. So this is supervised learning. We actually use A-star to train with this. Yeah, so this part, this architecture was supervised. We extended it to reinforcement learning later. So the motivation that we went for using the paper was, if you're doing something like this, if you try to do A-star for this, it takes forever. And what we can do is we can just train on A-star in this small map and get away with not having to do A-star in that bigger one. And that was the motivation. So it's not going to be better than A-star, sure, definitely, but at least you can have. So if we actually have something called A-star ratio, and it's pretty close to the A-star ratio. So the A-star ratio is pretty close to 1 for most of these tasks.
So based on what you just said about retaining information, that's very similar to what current networks do as well.
Yes.
Right. Can you pull up your architecture for can you talk a little bit about how this compares to the advantages of this over existing with current architecture?
Sure.
Tracking this as opposed to the more explicit numbers.
Okay. So this is your memory architecture. So what a recurrent neural network does is it puts together the memory computation and the policy computation in the same block. So you've got these C and H blocks, hidden state and an inner C state, which just put together both of these and you output policy. Now, what this DNC is doing is it's splitting these things together. So this block over here is called the controller. This controller is still a recurrent neural network. So this is actually an LSTM block over here. But what I'm doing is I'm splitting apart this memory computation and this policy computation, and by splitting these apart, this shows that this works. This is better than just doing all of these inside this little block over here.
How much engineering effort was it to transfer the policy from simulation to real world?
Oh, in this task, actually, it was very surprising. Not too much, because let me see what was different. Actually, yeah, it wasn't too hard. It was because we set up this in a very raw style environment. This is actually a ROS wrapper. We wrote an OpenAI wrapper for this ROS thing, and it was really simple to just take that policy and run it off on this thing over here.
Lighter simulation
Yeah. Yeah. So LiDAR actually transfers really well as compared to images. If you add some sort of Gaussian noise to your training process, to your LiDAR scan, and just model your real-world LiDAR as some Gaussian process, it works reasonably well. It's actually not that hard to transfer policies for LiDAR. For images, yes, it's really hard, but for LiDAR, it works reasonably well. Yeah.
For the tunnel experiment, you only showed environments that look very, very similar, and the optimal policy would just be to go left, half, and right. How diverse was the data set that you trained on?
Diverse in the terms of orientations, or?
Yeah, because here I could just memorize a single policy that would solve all of these problems.
Right. So we actually, if you look at the paper and the benchmarks, what ends up happening is it memorizes to learn at this fixed length. So your data set is just all these different tunnels, but they're all of this fixed length, 20. So your policy, if you do something like a recurrent neural network, what it ends up learning is I need to turn around at 20 time steps. So it learns this time information, but it ends up learning that I do this at every 20 time steps. Like if I've taken 20 steps, I turn around, and that's what it learns. What ends up happening in the test set is this is completely longer. It's never seen this. So if you use a recurrent neural network for this, what it would do is it go in 20 steps and then turn around without actually exploring the tunnel all the way to the end. If that helps. Does that make sense?
You don't really need memory for this, right? If your training set had different tunnel links, also a recurrent network would learn just so
Right. But then the limiting factor is still how long your longest thing in the training set was. If your recurrent network is learning that I turn around at X length. It doesn't learn how to turn around when I see that end of that tunnel. That's what the problem with the recurrent neural network is. We can continue offline. Yeah.